Our topic today is violation of OLS assumptions. And we're going to group the violations into basically 3 parts. So the first one is heteroskedasticity. Number 2 is multicollinearity. Number 3 is this specification errors. And here we can talk about different types of misspecifications. We have the one which is very famous, Omitted Variables Problem. Or let me be more specific and call it Omitted Variable Bias, because the bias is the problem, so bias. Number B is errors in variables. Number C is wrong functional form. And number D is simultaneous causality. Okay. So we have 3 main problems, and the last one we're going to be dividing it into different types of problems. So in each and every violation, we will be discussing about, or I will be kind of reminding you about what is the OLS assumption, what is the nice assumption made by OLS, and then we're going to drop these assumptions and see how our model is going to perform. So let's start with the first one, something that is very famous, heteroskedasticity. And OLS assumes that we have homoscedastic errors. What is homoscedastic errors? Homo is actually equal, skedastic is variance. So OLS assumes that we have equal variance. The variance of the error term is equal, or the variance of the error term is constant. And the shortcut is like the expectation of UI squared is simply equal to the expectation of U squared. We don't have to have a sub I because they are all the same, and it's equal to sigma squared, and this happens for all the i's from I equal 1 to 2 all the way up to n. Okay, so it's a critical assumption made by the classical linear regression model is that the error term UI all have same variance. Okay, it's a big assumption. Okay, so they all have the same variance, and this variance is called sigma squared, just the notation. And the problem is, if this assumption is violated, then, or if this assumption is not satisfied, then we have a heteroskedasticity problem, where hetero refers to unequal variance. Okay, so the problem is, if we have heteroskedasticity, so if I have, or in the presence of heteroskedasticity, how this is going to affect the best linear unbiased estimator characteristics. We know that the estimator to be blue needs to be unbiased. It needs to be consistent. It needs to be efficient. The heteroskedasticity is a variance problem, so it actually affects efficiency of the estimator. Okay, so I can have my estimator unbiased, which is fine because the heteroscedasticity affects the variance. I can have my estimator consistent, so in large sample it would approach the true population parameter with a high probability, but the problem is it will not be efficient. Okay, so what do you mean by that? We won't be able to get the lowest possible variance. So it's an efficiency problem. Okay, so no longer we will not be able to get the variance, or the estimators are no longer minimum variance. This is the biggest problem here. Okay, or they will be inefficient. To discuss this problem in more details, I wanted to recall how the variance is computed. So the variance of the error term, we have discussed this last week, is equal to the sum from I equal 1 to n of how far each estimated error for each observation is far from the estimated error bar, and this is just the computation of any variance, divided by the adjustment of degrees of freedom n minus how many regressors k minus 1 for the intercept. We can actually simplify this notation by getting rid of this term, because this term in OLS, or the mean of the error term, or the expectation of the error term, which is simply equal to the sum from I equal 1 to n of ui hat squared. Sorry, it's not squared, it's just ui hat over n. It's just the computation of an average, is 0. So this is an OLS assumption. The assumption is just telling us that I might have just, this is the scatter plot here, and this is the estimation of a regression between y and x. I can have error terms above the line, below the line, above the line here, but their average, the average of all these error terms, is equal to 0. This is the assumption. Okay. I want you to note that the expectation of the error term, or this part, is not our main issue in heteroskedasticity. Our main issue is actually the variance. So I'm just reminding you of this because I can now get rid of this part because it's assumed to be 0. So I can rewrite this formula by saying, okay, so the variance of u is simply equal to the sum from I equal 1 to n of u I hat squared over n minus k minus 1. And this is something that we already know. It's the sum of the squared zeros, SSR, over n minus k minus 1. Okay, so this is the variance that is assumed to be constant. It's assumed in OLS, assumes that this variance is constant. Okay, doesn't change, so it's just constant, and they call it just the sigma squared. Okay, so if you also apply this to the simple regression model, so if you apply this to a simple regression model and say, okay, the variance of my dependent variable given x is equal to the variance of the intercept given x plus the variance of the partial slope of the first, or the regressor xi given xi, okay, plus the variance of the error term given xi. So what is this called? This is the conditional variance of the dependent variable of yi given a certain value of, or given xi. Okay, so let's check each part. So this part is telling me what is the variance of something that is constant, something that does not change. It could be 5, it could be 4, it could be just any number, given certain value of x. Let's say x is age, and this is your salary. So what is the variance of a number, which is probably 5, 6, any number, given my age is 16, right? So it doesn't make any sense. So this part is just equal to 0, since beta naught is a constant. Next, what is the variance of beta 1 xi given xi? So it's again 0. Why is it 0? Because xi is given, it's not random. So now we can get rid of the second component. Okay, so we are left with just this part. So this is to tell you that whether you look at the variance of your dependent variable given xi, it's actually the same as looking at the variance of your error term given xi. They are just the same. Okay, they are just representing each other. And since the OLS assumes that ui and xi are independent, then I can just make this link, right? This is a conditional variance of the error term given xi. If they are completely independent, then I don't really need to condition on xi, and I can just make my life simple and write it this way, okay? So next, if the OLS assumes that the variance of the error term when the observation is equal to 1 is the same as the variance of the error term when the observation is number 2, and it's the same as the variance of the error term when the observation is number n. So these are all the same. So I really don't need to have a sub I here, and I can make my life even simpler by just typing, okay, it's u. And sigma square, okay? So this is all just kind of the background of what we want to see or what we want to check. So all I need to check is in each and every model I'm doing, I need to check this connection. Is there any connection between the variance of the error term of the model and the x's in the model? If yes, then I have heteroskedasticity. If no, then I have homoscedastic model. So we can actually kind of like write it in this way. If the variance of the error term given x is constant, this implies homoscedasticity. And if the variance of the error term given x is not constant, then I have heteroskedasticity. Okay? And I can check that by just like one of the ways to do that is just check a graph. And suppose that this graph has here the error term of the model square, and here I have the x. And if I graph this and I get something like this is the scatter plot, right? And just by looking at the scatter plot, I can see that as the x increases, there is actually no increase in the error terms, just I can group these into kind of an interval that is almost constant. If this happens, then this is just homoscedasticity, okay? It doesn't have to be like in the positive part, it could be like in the around the 0, like down here, but it's a square, right? So it's going to be positive, but I mean, like, it doesn't have to be all the way up. It could be like a little bit below, a little bit high, and so on. Any other form of a graph that is UI hat squared, and this is the X, and it's taking kind of an inverted U shape, or it's taking a U shape, right? This is heteroskedasticity. Same here, this is heteroskedasticity. If I have any other form of relationship, right, it doesn't have to have a certain shape, but it's not constant. If I don't get this, then it's heteroskedasticity. Okay, and this is just kind of an informal way of checking whether your model has heteroskedasticity or not. And in higher level of econometrics courses, you would be actually performing formal tests. For the requirement of our course, we will be performing a couple of tests that we will go over now. But we have also kind of more sophisticated, more formal tests that can be performed in higher level of econometrics. Okay, so the problem is when I have heteroskedasticity, I said already that in the presence of heteroskedasticity, so if we have heteroskedasticity in the model and we keep or we kept on using the same OLS formula, I would have misleading results, because now the standard error computed in my regression is not the correct standard error. So if I checked and I felt like, okay, the graphs are telling me that I do have heteroskedasticity, and I was still continuing to use the same formula for the standard error of the coefficients, then I would have misleading results. I want you to understand that the computation of the standard error is just part of the computation of the t-statistic, and the t-statistic is part of the p-value. And again, the standard error is a part of the confidence interval. So if I have standard error that is wrongly estimated, then this would have multiple consequences on my measures of fit. And would be probably showing me that a certain coefficient is statistically significant while it's not statistically significant, and the opposite is true. Okay, so in the presence of heteroskedasticity, then we have to use, or we have to change the regular standard error used, okay, in OLS estimation. So the one that is used in the OLS estimation, this one would be wrong. So we have to use a different standard error. This one is wrong because it does not allow for possible dependence between the variance of the error term and the x's in the model. Okay, it just assumes they are totally independent. But however, if they are dependent, then I have to include a certain term to account for the dependence, to account for the correlation between these two terms. And if I don't do that, then I will get misleading results. Okay, so the misleading results would be if you have different misleading results. So the t is affected, p-value is affected, right? What else? Confidence interval is affected. Actually, the F test is affected. All these are misleading. So if I do have a heteroskedasticity, and if I don't change my standard error, I will get misleading results. So what you need to do is you need to use a different standard error called robust standard error. And the robust standard error, I'm going to show you the equation. The robust standard error accounts for the possible correlation between the error term and the x's in the model. All right? So the robust standard error so it accounts for the possible correlation between the variance of the error term and the x's in the model. So it corrects for the heteroskedasticity that we have in the model. Okay, I want you to recall that the variance of beta when we were using homoscedastic or in the general OLS, just the standard error, was like this. So the standard error when the variance of beta had in the previous topics, we used to have it like SSR over n minus k minus 1 over the variance of x. Okay, so this is how we used to compute it. Okay, and suppose I have multiple x's, so you can have it like, okay, if this is j, this is beta j, and this is xj. Okay, or beta I and xi, whatever. So now, with the presence of, just let me make this xj, okay, and now, or you can actually write it in a population notation, given that I already gave you the population notation on the first slide or the second slide today. So you can write this one as equal to sigma squared over, right, the sum of xi squared, okay? So in this way, you can actually call this one as the variance of beta j homoscedastic. Okay, so the homoscedastic variance here does not account for any possible correlation. What you see in the numerator is just a certain number, which is called sigma square. And if you actually compute this, it's going to be just a number, right? Sum of the square residuals over n minus k minus 1 over the variance of xj, divide these by 2. Like they're just going to be a number that is constant, okay? Now, if I want to check what's going to happen in a heteroskedastic case. The heteroskedastic case is actually, and we're assuming that you have heteroskedasticity, then it's going to be equal to the sum of xi squared ui hat squared over the sum of xi squared whole squared. So now this variance is accounting for, right? It's accounting for possible correlation between xi and ui. So anytime I do my tests and realize that there must be a connection between the variance of the error term and the x, then I do have to use the heteroskedastic standard error. This is the variance, but you already know that you can get the square root of this and get the standard error. And this is going to be the robust standard error. So the robust standard error is just the square root of this formula. Okay, so reasons of getting heteroskedasticity. Okay, why I can have heteroskedasticity. So some of the reasons, like there are multiple reasons, but I'm just gonna go over the most important ones. So some of the reasons of heteroskedasticity are the following. One of the famous source of heteroskedasticity is presence of outliers. So what is the presence of outliers? I do have, for example, X and I do have Y. The relationship like of the scatter plot, like let's say, looks like this. Most of the observations are within a certain range, which is fine. What about if I have one of the observations are right here, or one of the dots are right here? So if you can think of an oval shape that combines most of the observations, then anything that is outside the data range, like this point or any other place that is outside the range of observations, if I'm trying to, let's say, fit a line of the regression here that is telling me this is the estimated population regression line, and each and every distance between this dot, for example, and here is an error term, this dot, and here is an error term, this dot, and here is another error term. But what about this one? This is a huge error term, right? This is again a huge error term. So this distance and this distance are actually reflecting a large error term for this specific observation, and it's coming from the fact that this observation is way outside the range of observations, and we call it an outlier. So this outlier would actually affect my result because it's going to be telling me that you have a large amount of, because by the end of the day, I'm just getting an average of all my errors, and it's going to be kind of magnifying the amount of errors I have in my estimation. Given the fact that heteroskedasticity is actually related to the error term, then this is going to be affecting my test of heteroskedasticity. It might be telling me that I do have heteroskedasticity, while if I can just drop it from my regression, then I won't have any heteroskedasticity. I have a homoscedastic model. So the one thing that you can do before you start your estimation is just to graph your data set. Graph your data set, make sure that you don't have any outliers. And if you do, you go to these outliers and try to study it. Is it something meaningful? Is it something related to a change in policy by the government? Is there any increase in interest rate all of a sudden based on a decision by policymakers? Is it related to an increase in money supply? Is it something important? Is it related to the coronavirus? Something like that, right? And if it is something meaningful, then you would keep it and you explain it in your model. If it is something that is like not important, or is probably related to a mistake, you downloaded your data set and all the observations here are in dollars, but you kind of made a mistake and this one is in cent, right? So you can correct that. So if you cannot correct it and it's not important, you can just get rid of it, okay? And it would be like an easy solution. You're just deleting it from your data and then you're running or you're re-estimating your model. So this is one of the things that are very famous, and you will see it a lot, which is the presence of the outliers problem and how it's creating or how it's leading to heteroskedasticity. Number two, this is again one of the very famous sources of heteroskedasticity, and this is called the misspecification. Misspecification of the regression model. What is the misspecification of the regression model? This is something that we will discuss in detail, more in details today. So suppose that I'm estimating this model. Demand for good X is a function, has a certain intercept, is related to advertising, right? And for good X, okay, plus alpha 2, the price, plus the error term. Okay, so everything here has sub-I, it's a cross-sectional data set. So it moves, suppose that you're doing this for a group of, let's say, stores, and you're trying to estimate the demand for milk, for example, or certain brand of milk or certain brand of cheese as a function of advertising, how much the company is paying for advertising for the specific brand of cheese or anything, and then the price. Now, suppose that this is the correct model. Now, suppose that you decided to estimate this model. dxi equal to alpha 0 plus alpha 1 advertising of good xi plus, let me have another name for the error term, vi, okay, where vi is the error term for regression number 2. Suppose that this is like the wrong model. It's wrong because you forgot a very important variable for your demand function, which is the price. And if you forgot this, then it's actually going to be picked up in the error term of this regression. And this error term is going to be equal, di is equal to alpha to the price plus the error term of the previous regression. Okay, so what does that mean? It means that I'm creating a connection between an included regressor, which is advertising, and the price. There must be some connection between these two. And now I'm kind of creating a connection between advertising and the error term of this regression that could be not constant, right? I might have positive, it might be negative, and this is the variance. Let me call this the variance of the error term of model number 2. So if you have done a misspecification error, if you wrongly specified your model, knowing that price is an important variable affecting demand from our studies of microeconomic theory, and then all of a sudden you forgot to include it, and then you have a wrong model and you estimated the wrong model, you have created by yourself a heteroskedasticity in the model. And just remember that heteroskedasticity is not just that you have a correlation between the two, between the error term and the included regressor, but it's also about the variation of this error term, right? I'm saying the variance, the variation of the error term with the included regressor. There might be a significant connection between the two, right? It might be also connection, but insignificant. So we need to test that. We need to test whether it's present, there is a connection that is present, and if it is present, is it significant or not? Okay. The other thing is like the other source, and this other source is, or the other source of heteroskedasticity is actually something called the error learning models. What is the error learning models? So the error learning models is basically saying that as people learn, and you can apply it for yourself, on yourself, whatever errors you make decreases, right? So the errors of behavior will become smaller over time. And you can apply this, for example, to you are learning it's anything. You can be learning, let's say, typing, right, on the computer, blind typing, for example, and you want to see how your errors decrease over time. Okay, so this one is telling us that the variation, let me say, this is the variation, let me say here the variation because it's not just the error, the variation of errors decreases over time. What is the variation in my errors? Let's say today I try to type many hours, and then what is the average of variation over the day? Then I'm trying to do that again tomorrow, and then after tomorrow, and then I'm comparing the variation of errors over time. And it's expected to fall because we learn from mistakes, and this is basically saying that the variation of error decreases over time. Okay, this is just an example. Another thing that is actually about the improvement of data collection technique. Okay, so as we have improvement in data collection techniques, then the variance, right, of errors decreases. And this is actually this paper was related to the monthly statements of, like, these were banks, and the banks were trying to see how the improvement in data collection would reduce the errors in the statements of their customers. Okay, so so we said that improvement in data collection techniques leads to a reduction in errors in the monthly statements of their customers. Okay? So we're talking about banks. And this is, again, another source. We will focus actually on 1 and 2, okay, because these are more related to our econometrics, but I'm just also letting you know the other sources of possible changes in the variations of a certain variable. So let's go to how to detect, or how can I detect it, or how can I test. So how to detect heteroskedasticity. Okay, so there are different things that we can do, and then again, as I told you, there are things that are complicated that we can use to check, but for the requirement of your course, we're just going to do like few things that are relatively less challenging. So number 1 is graphical method. Okay, and the graphical method is, as I kind of showed you here, what we need to check. We need to check this variable with the x's that we have in the model. So I need to check the variance of the error term against the x's I have in the model. If I have x1, x2, x3, and so let's say multiple x's, then I'm going to have, let's say, x1, x2, x3. So I'm going to have a graph for each x. Okay, so to do that, we actually need to extract the error term. So the graphical method would be graph ui hat square against, you have multiple options, okay, against yi hat or x1 or x2, and keep going, right, xk, okay. And I want you to remember that this is actually kind of a summary of those, because this one would be including like beta 0 plus beta 1 x1 plus beta k xk, and these are all estimated. So we have the hats here. So you can either do it this way, kind of a shortcut because it includes all the x's, but it would give you like the overall picture of whether I do have connection between the error term squared and the estimated yi, or the linear, you can call it the linear combination of the x's, but it will not tell you what is the source of heteroskedasticity. Is it x1, or is it x2, or is it x3, or is it xk, or they are all, or just one of them, and so on. So some people, they would do this one to get the overall picture, and then they would do like the more details to get the picture of what's going on in the each x. Okay, so you can like do this ui hat squared, and then this is yi hat, and suppose that you got like some relationship that could be positive, let's say. All right, so now you want to get more details, so you would be like, okay, let me do each x. So this is xk, this is x3, this is x2, this is x1, ui squared, ui squared. So I still have on the y-axis the same variable, okay? And then suppose I found this one to be homoscedastic, I found this one to be heteroskedastic, heteroskedastic, homoscedastic. Then I would understand that this problem is coming from x2 and x3, right? So what I really care about is the, let's say if I have it from x2 and x3, then I have some heteroskedasticity in the model, then I would definitely need to use the robust standard error, okay? If it turns out to be the case that, okay, doing this and I have homoscedasticity, so the relationship is kind of, doesn't seem to be positive or negative, it's just kind of a straight line, then I would have to go to each and every, right, x, and it might be like, okay, an easy result where I do have each and every one is just doesn't seem to be homoscedastic, or it could be actually one of them is homoscedastic, but insignificant, right? So if it is insignificant, then just forget about it. And that would brings us to our next test, which is about significance. Here I'm just checking with my eyes, right? Like just looking at the results graphically and deciding just looking at the graph. But I personally prefer to complement whatever I see in my eyes with a certain test. So the test that you can do is okay, number 2, to do a regression. Okay, so in order to do this regression, you will have to, a regression of what? A regression of ui hat squared on, I can do it on yi hat, or x1 on x2 on xk, or on x1 and x2 only, or like you can choose whatever set on x1 and xk only. So you have different options. Again, this one would be your summary, right? Because this is the linear combination of the rest. Or you can be like doing some details, taking each one separately and doing the regression. But then after I'm doing this regression, what I need to do is I need to actually get the R square of the, I need to get the R square of the regression. So you do the regression on either yi hat, on x1, x2, or a combination of any x's you want. So this is like your choice. And after you're done, you actually need to, so you already know this. Okay, so on x, on y, or just going to clean this. So you do it on yi or x1, keep going, or xk, or any linear combination. Okay, you prefer. Okay, and then after you're done, get the R square of the model. So I want basically to know what is the explanation of this regression. And of course, I hope that I have a very low explanation. I said before that this R square ranges from 0 to 1, where 1 is 100% explanation of the model and 0 is 0% explanation. So actually, I hope to be kind of very close to the 0, okay? After you get this R square, you compute something in R square. So you get your number of observations, okay? You get your observations, and this is the R square of the model, whatever model you decide to choose, and you get this statistic, okay? And you compare it with the chi-square critical value, okay, from the table. So you go to the chi-square table, you need to find out, okay, what is the critical value. And what I have here is Q. What is Q? Is the number of coefficients under the null, or number of coefficients tested. So for example, if I have a model like this, Ui square is equal to alpha 0 plus alpha 1 x1 plus alpha k xk, and I want to check the R square of this model, and I got this R square, then I multiply it times n, and I want now to compare with the critical value of the chi-square table. So the Q here, the number of restrictions, is how many coefficients I'm testing. I'm testing 1, 2, 3, 4, k. So I'm testing k coefficients, right? I'm testing k coefficients. So what you need to do is you need to determine how many coefficients you're testing, okay? And what you're testing is like this. You're testing the null hypothesis that alpha 1 is equal to alpha 2 is equal to alpha k is 0. And the alternative is simply like an F-test. One of above restrictions does not hold, okay? So you actually, you hope to fail to reject, okay? So what you are going to conclude is you check this n times r squared, okay? And if it is less than the chi-squared with 2 degrees of freedom, so let's say like this, here this is the rejection region, this is your critical value, okay? And suppose that, or here I'm calling it the chi-square with 2 degrees of freedom, critical value. So this is the CD, critical value, critical value. So suppose that this is, I got something here, this is the acceptance region, or the no rejection region, and this is the rejection region. So if this one is less than this one, my conclusion would be do not reject the null. And if I go back here, what is the null? The null is that these coefficients are equal to 0. So that's the good news, right? So if these coefficients are equal to 0, then I have homoscedasticity, right? So I want you to imagine that you can actually make your life easy, and right here, if I get this one, this is homoscedastic. If I get this one, then this is heteroskedastic. So if I have a high p-value for this one, then I have homoscedastic. Or if I have n times r squared is less than the critical value, so again here, I'm failing to reject, so I have homoscedasticity, and the opposite is true. Okay? So before we leave this part, let me show it to you in Stata. Okay? So in Stata, let me share with you the desktop again. Okay. So let me just minimize this one too. And okay, so this is the do file. I have updated this one to include everything we're doing today. So let's see. What we have here, I have like multiple checks that we will go over, but let's go for the heteroskedasticity. Okay. All right, so we're gonna start from here, heteroskedasticity check. Okay, so here we have the model of consumption, income, and population. So let me get the data set first. So we need to clear whatever I have, get the new data set, and we have 37 observations, a very small data set, 11 variables, and it's a time series data set, so we have to declare it, okay, as being a time series. And let's go to our model. We're doing a simple regression, how consumption is affected by income and population. Now, I want to get the estimated C hat. It's like what I was explaining, and I'm saying, if I want to check whether I have heteroskedasticity, I can check for the relationship between the error term and y hat. So this is my y hat. To get the predicted dependent variable, you actually have the predict command. So the predict command is going to give us the dependent variable, the estimated dependent variable, okay? And next, I also want to get the error term. I'm going to call it error hat. You can call it your main, okay, anything. And then this is very important, comma, residual, because this is a part of the command. And this one is telling Stata, get me the error term, which is called residual here, and call it error hat. So we're going to get the error hat because we need it. Now we're going to do the graphical test, how the error hat is related to the y, okay? And as you can see, right, the residual and the y, it's kind of moving down and then kind of getting, it doesn't seem to be constant, right? It doesn't seem to be just fixed. But again, just this is what we see by our eyes. You can actually do it with each x, right? So if you do it with the population, see, like it again, it's going down, doesn't seem to be constant, right? There is a spread all over the place. This is probably an outlier here, but it doesn't seem to be constant, okay? Next, if you also check with the C hat, which is the Y hat, right? It's giving us also the same kind of graph, similar kind of graph. So just by looking at the graph, okay, so we can say that it seems like we have heteroskedasticity, okay? I also have, okay, so here I'm telling you that if I conclude that by just looking at the graph, if you have a question and I'm asking you, just use the graph to determine, okay? And if you use the graph to determine whether you have heteroskedasticity or not, then you can, and if you decide, okay, I have heteroskedasticity, then you need to use the correct standard error. And the correct standard error, which we call the robust standard error, the robust standard error is actually, so it's called the robust standard error, like the one I showed you on the slide. I mean, like on the iPad. The robust standard error, you can type R or you can type robust. It allows for a possible covariance between the error term and the x's of the model. Okay, and if you run the regression now with the robust standard error, then it would be reflected here. This is a robust standard error, and if someone looking at your output of the regression output, they would understand that you are correcting for heteroskedasticity problem by using the correct standard error, which we call it the robust standard error. Okay, let me also show you another model where we're using the NR. So I'm using here the college distance data set. So I'm going to use another data set. And this data set is trying, like the main idea of this data set is you're trying to estimate the factors affecting education years or years of education, right? And there are different variables and you have the explanation of, or the data description on Sakai. So let's, one of the variables is distance to college, tuition, unemployment rate, the result of a by test, and so on. So just the regression here. And then again, we're just doing exactly, we want to extract or we want to get the error term. This command is exactly like this one. Let me go up here. This one, right? Predict error head residual. I'm just writing it in a different way so you understand that you can either write residual, or just R, okay? You can name it error head or residual, whatever you like, okay? So it's just like different variations of the same command. And then now we got the error term. Now let's square it. Just notice that here I didn't square it, but you can also square it, like you can square this term and then repeat. You will get the same result. And then now we want to generate the square term of the residuals. So it's going to be like error squared. So you get the error squared, and then you want to use it in order to do the test. So let me first go with the test. I'm going to go with B, and then I'm going to show you A. So in number B, what we're doing is I'm getting the error term squared, and I just chose one of the x's, okay? You can repeat it with this one, and then this one, and this one, and this one. I just did it with one of them, but you can repeat. So you get this one, okay? You do the regression, and this is the relationship between by test and the error. And it's actually, this is a bad news. It's just telling me that there is a significant coefficient between by test and the error term, right? So there might be connected here. So if you go to, it's actually, I'm just referring to the slide so that in case you're lost. So if you check here, slide 29, here is the test I was telling you. You get the error term from this regression. Here I'm doing it on the y hat, or this model is done on the y hat, but you can always do it with the x's or the y hat. You can keep repeating it and so on. So you want to get nr square, and you want to check whether it's greater than the chi-square, okay? Here we have just one coefficient to be tested, so that's why the degrees of freedom is 1. So, okay, so we need to use this r square, the one that you see it here. We're going to multiply times n, which is the number of observations, and I've done it here. So I'm generating new variable, I'm calling it nr, and nr is equal to the number of observations I see here, right, times the r squared, okay? Just notice that you cannot have any commas in here. And then I'm displaying the results. Displaying is just a nice way of presenting the results. So I'm displaying the output. So what we got is 94.1408. Now, how can I determine whether this number is bigger or smaller than the critical value? So I need to go to the chi-square table, and the chi-square table is, I chose 5% significance level, but you actually, you can choose whatever significance level you like, as long as I'm not asking you in a question a specific one. But the result is going to be the same, whatever significance level you choose, okay? Because the number that we got is 90 something. Here, our critical value is 3.84. So 3.84, and the number that I got is actually way above the 3.84, right? So what we're gonna conclude is we are going to reject the null hypothesis and of constant variance and conclude that we have heteroskedasticity. Okay. Also, there is for the graphs, there is a nice command in Stata that you can use. You can either just type graph, scatter plot, like what I did here, scatter. I get the error hat and with the y, which is x1 with x2 and then y hat. You can actually also use something called RV, residual plot, and F here stands for the fitted value. What is fitted? Fitted is the y hat. And you can just graph this one. And as you can see, like it doesn't seem to be constant, right? So the RVF plot doesn't show us a homoscedastic graph, like it's spread all over the graph here. It's not constant. If I would get it like somewhere around the 0 up and down, then I would be able to say, but this one looks like something that is high and then getting smaller and smaller and smaller, meaning that as the fitted value increases, the residual is decreasing on average over time. But it's not constant. So it's heteroskedasticity for sure. Also, if you use the RVP plot for, let's say, for one of the x's, let's say by test, you can actually repeat it with all the other x's. Again, I'm just doesn't show us any homoscedasticity. And if you repeat the same with the other one, then you will get a similar graph. Okay, so the two tests that we said are basically you can do a graph, right? Whether it's a scatter plot, whether it's a line graph, whether it's a RVF plot, it's up to you. And the other one would be the test, which is the NR test. Okay, NR test is explained on slide 29 of chapter 13, and you can, and we're doing it right here with different data. So, all right, any questions? Any questions? Okay, good. So our next violation of OLS is called multicollinearity. So let's talk about multicollinearity. I'm going to go back to my iPad and we're going to discuss the next one. And this is our second violation, which is number 2. So multicollinearity. Multicollinearity is the collinearity between the x's of the model. So it's related to the independent variables in the model. So if I do have a model like this, yi is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus ui. The multicollinearity problem is all about the connection between the x's, right? How x1 is correlated with x2, how x1 is correlated with x3, how x2 is correlated with x3, and so on. So it's not like our previous violation, which is heteroskedasticity, which was related with the error term, right? Now it's more of a problem related to the x's. So let's say if I have, let's have this notation, the correlation between x1 and x2, okay, is equal to the correlation between x1 and x3, is equal to the correlation between x2 and x3, and it's equal to 0, then no problem, okay? So no multicollinearity problem, right? So there is no problem, right? So that's perfect result. Okay, there is no connection between the x's at all. And I can get estimation for beta hat 1, beta hat 2, beta hat 3. They will be all correctly estimated, so I won't have any problem. The problem would arise if I have a non-zero correlation. So if the correlation is not equal to 0, then I have a problem, okay? Then I have to deal with it. So if I do have, for example, let's say I have like different, if the correlation between 1 and 2 is the same as the correlation between 1 and 3, and it's equal to 0, but the correlation between 2 and 3 is non-zero. So if this is the case, then I don't have any problem, no problem in estimating beta hat 1. Right? There is no problem because x1 is not correlated with anyone. So there is no problem in the estimation of beta 1. But here, there will be a problem in estimating beta 2 and beta 3, because if x2 and x3 are related with each other, then these two would be affected. Their estimators or their impact on the y would also be affected. Okay, so let's start with talking about what the OLS assumes. So the OLS has this like nice assumption no perfect multi-collinearity. Okay, so no perfect, no 100% collinearity. Okay, so this is their assumption. So for example, how can I make it perfect? If I do have a mistake by estimating, let's say, x1 plus beta 2 x1 again plus 2i. So I'm repeating the variable twice here, and this would create a perfect multi-collinearity. Okay, so when it creates a perfect multi-collinearity, then the good news is theta would drop one of the x's for you, would tell you, okay, it's repeated, okay, and would estimate for you a model with just one time x. All right, so this is one of the assumptions. However, OLS can allow for the imperfect, okay? So imperfect multicollinearity, let's say something that is less than 100% is allowed, but not preferred, of course, but it's called the imperfect. So the perfect is when the collinearity is 1, correlation is 1, but anything that is less than that is called imperfect. And of course, the more I approach to the 100%, the more is the multicollinearity problem. Okay, since we are not assuming that we're doing this mistake of a perfect multicollinearity, so from now on, when I say multicollinearity, you understand that I mean imperfect one. And when I kind of get closer and closer to the 100%, then we have a problem, okay? And we need to minimize this multicollinearity as much as possible. So let's talk about the sources of multicollinearity. So for the sources, of multicollinearity. Number one, there is something called model specification. So, for example, if I'm estimating a model where I have yi is equal to alpha naught plus alpha 1 xi plus alpha 2 xi squared, right, plus ui. So the way I'm specifying the model by adding a polynomial term that is actually made of xi is going to lead to multicollinearity. Okay, so whenever you have a model in which you're adding a polynomial term of the variable or an interaction term of the variable, then you're kind of creating a multicollinearity. However, we just want to make sure that you also understand that whenever I have a polynomial model and like this, for example, or even higher term like to the power 3 or to the power 4, whatever, this is not the like it's a multicollinearity problem, yes, but it's actually we made it, right? We made it in the model. We are the ones who have created x squared or x cubed, and it's not a variable that is coming to our model by chance. We want to focus on the variables that are coming to our model by chance to call them as a problem. If I have something like this, yes, it's a source of multicollinearity, like based on graphical representation or a test or something, I will be able to find high collinearity between x squared and x because they are actually the same variable. But this is not our main concern. Our main concern would be a collinearity between x1 and x2, two variables that are here by chance and they happen to be correlated. So if this is your salary and this is your age and this is your education, there is a correlation between age and education years. As the person gets older, of course, I expect more years of education are correlated with the age. So if I'm trying to find this correlation, whether it's significant, is it too high, then these two variables are coming by chance. They are not made out of each other. But anyways, I do list this as a source of multicollinearity because if you perform the formal tests, you will be able to find a high collinearity between the two. But just understand that this is not our main concern. Number 2. And overdetermined model. What is an overdetermined model? Okay, an overdetermined model is a model that has the number of the x's, okay, or the number of independent variables or exploratory variables, right, are higher than of observations. Okay, so if I do have number of x's, the number here is, suppose I'm just making an assumption. Suppose I do have, let's say 10 x's, 10 variables in the model. And I have only 9 people I'm asking. Okay, so my list of observation is just n, which is just, I have only 9 people I'm asking. So I have 9 patients to whom I'm collecting a large number of factors affecting whether they are cured from certain medication or not. So if this is the case, this is called an overdetermined model. And again, I'm not considering that we will go into this problem because all the time we're talking about the advantage of a large sample size. So we will not run into a problem of just getting number of observations that is equal to just 9 or a small number of observations. We all the time trying to get a bigger and bigger and bigger number of observations. And also the number of x's, we never run into 10 x's, but we usually, like the default is between 5 and 6 variables as considered as the variables that have a major impact on your dependent variable. So this is just a source of multicollinearity, and to overcome this source of multicollinearity, you can just increase your observations, right? Increase your sample size. The last one So number 3, it's data collection method. And what is the data collection method? If I'm just talking about, let's say, interest rate, and the interest rate is, let's say, was 3, 3.4, 2.9, 3, 2.4, 2.2. As you can see, I have a limited range of observations taken by the independent variable, right? So as you can see here, when I talk about, let's say, the variable interest rate, I can say, okay, it's just like taking a small range from 2.9 to 3.4. If I'm sampling over a limited range of observations taken by the independent variable, then I would create a multicollinearity problem. I don't have like large variations in the numbers taken by the independent variable. So this one is actually coming from the fact that you're sampling over a limited range of values taken by the independent variables, or let's call it regressors, right, in the data set or in the population in general. Okay, so I have a limited range for the interest rate, or I do have a limited range for income of the consumers in my data set, or I have a limited range of inflation data set, and so on. If I have a limited range of any variable, then I'm creating multicollinearity, because it is right, I don't have much information here. And to overcome this problem, then just you need again to have a larger data set, so you have more information, you have more variations in the variables understood. Okay, so how to detect the multicollinearity problem. So let's first talk about the main consequences of multicollinearity. The main consequences of multicollinearity is, again, when I talk about consequences, I want to just recall that I have the best linear unbiased estimator that is consistent, that is unbiased, that is efficient, right? So I need to check the consequences of the problem by what's going to happen to these 3 criteria. The multicollinearity problem is, yes, going to affect the consistency and the unbiasedness, but the huge impact is actually, again, on the variance. It's a variance, again, problem. If I have a multicollinearity between 2 variables, it would be actually reflected in the computation of the variance of the coefficient. Okay, so again, I would have some impact here, right, on the coefficient itself, but the huge impact would be sensed in the computation of the variance. Okay? So you can say that if I'm talking about the t-statistic, or if I'm talking about beta hat minus beta 0 over the standard error of beta hat, and this is like J and this is J. So the multicollinearity problem affects the estimator and its standard error, which is coming from the variance. The huge impact actually is sensed here. So one of the ways to check or to detect the multicollinearity is to detect what happens to the variance of the coefficient. Okay. So the main consequences are, one, large variances of the betas, or same betas, but coefficients. This is number one. Number two, I want you to imagine how these variances are connected with everything. You know that already. It's connected with the t-statistic, the p-value, confidence interval, everything. Right? So you would have the confidence interval, which is equal to beta hat plus or minus the standard error of beta hat times the critical value, CB critical value. So this one, if this one is affected, my critical value is also affected. Okay, I said that this one is going to be affected, but it's minor effect as compared to the huge impact that is going to be seen in the standard error or the variance of the estimate. So this is like the bigger, it's going to be big or large in the presence of multicollinearity. Okay, okay, what is the consequence of that? I said that because the t-statistic, let's go back here, so this is number three. So number three, because the t-statistic is the difference between the standard error of beta j, okay, if this is affected, if this is big, if this increases, then the t-statistic would fall, okay? So I might have a statistically significant coefficient, but because of the presence of multicollinearity, then it turns out to be insignificant. The t-statistic falls below the critical value of t-statistic. So it's we're getting into the range of acceptance region, turning a coefficient that was supposed to be statistically significant to insignificant. Okay, so you can say that one or more of the coefficients are insignificant. Okay. Number four, this is like, what about the R square, which is the explanation of the model? You're actually gonna have a high R square. Okay, so the high R square is telling us that I have a good explanation of the model. So you have kind of mixed results. Good explanation of the model, low t-statistic, or good explanation of the model, insignificant coefficients. This mix is a good way to detect heteroskedasticity, good way to detect multicollinearity. Okay, the R square is high. The F statistic is also high, telling me that the coefficients of the model are jointly statistically significant. Right? So in order to detect multicollinearity, I'm going to use these consequences as a way to detect multicollinearity. So you need so how to detect multicollinearity? So you need high R squared, which is actually a nice result. You need to have high F statistic. You need to have low T statistic. And this one is telling me insignificant coefficients, high explanation of the model, coefficients are jointly statistically significant. Okay, if I have like this kind of blend together, then this is okay. There is a problem. Okay, there is a multicollinearity problem. Of course, this is just by detecting, like just looking at the output of the results that you get. But you can also do something that is simple. So let's call this one as number one. Just check the output that you have. If you have this mix, then this is indication of a multicollinearity problem. The other thing that you can do is you can check the correlation table. Okay, so you check the correlation table, which would provide you correlation between the different x's in the model. There is no benchmark here, but if I do have something that is, let's say, higher than 80% correlation, then you have a problem. You have a multicollinearity problem. So there is again no benchmark, but let's say if you see a number that is 80% or more, or actually I would like, when I was doing my dissertation, I had one of the variables where it was like 50% and I still said, okay, it's a problem. Okay, so you try to avoid the correlation between this correlation between the x's as much as possible. Again, this is just by checking the output. This is an informal test. In a higher level of econometrics course, you would be taking more formal tests to detect multicollinearity problem. Also, an informal way of checking multicollinearity is, let's say, check what happens to the model every time you add an additional variable. So let's see. I have yi equals alpha 0 plus alpha 1 x1 plus ui. I estimated, let me write it in terms of an estimation so I don't need to. So I estimated this model, and then now I'm adding a new one. Alpha 0 plus alpha hat for x1 plus alpha hat to x2, and of course you need to have the sum I everywhere. Okay, so if I'm adding x2, I need to check what happens to alpha 1. So I already can see the value of alpha 1. Is adding x2 has a huge impact on alpha 1? If yes, then I have multicollinearity. If there is no effect, I cannot sense any effect when there is no multicollinearity issue between x1 and x2. Okay, so this is just by having a model, estimating a model, and then throwing in another variable, seeing what happens to the estimated coefficients. You also need to check what happens to the standard error of alpha hat 1 in model 1 versus model 2. If it increases, then yes, there is a multicollinearity, because I said multicollinearity problem has the huge impact on the variance or the standard error of the coefficients. Okay, so this is another way of checking the multicollinearity problem. So now let's move to Stata so that we can see how we check multicollinearity in Stata. Okay, so if I want to check multicollinearity, this is the heteroskedasticity. Okay, let's see this one. Okay, so here what I have is, okay, let's use the, again, let me clear using the consumption, declaring time series data set. Now I have a model in which I'm estimating how income affects consumption, how the increase in population affects consumption. So this is our base model, okay? So our base model is like here, and we're estimating this regression. Everything seems nice. So income has a statistically significant impact on consumption as expected. It's positive as expected. Population is, the increase in population also increases the aggregate consumption, statistically significant and positive as expected. So everything seems okay, seems nice, seems as expected. Now, let's try to add the real disposable income and see how it affects the results. So if I start to add this variable right here, what I can see is what happens to the already included regressors, okay? So when you compare the y, I don't see a big change in the standard error. This is 0.48 and it used to be 0.45. So there is no big change in the estimated standard error for the y variable. Let's see the population variable. Here was like 0.058 and now it's becoming 0.08. So it's like there is a huge increase here. I don't have the percentage jump in the standard error, but it seems to be big. So now, because of the huge increase, and also you can see that there is a change in the coefficient of population, but the change is not as huge as the change in the standard error. So the t-statistic, which is this one divided by this one, has been affected, right? So there is an increase here, but not as much, but there is a huge increase here, making the coefficient that used to be statistically significant now insignificant. So this is a sign of multicollinearity, and it would be important to check whether I do have multicollinearity or not. So what you can do is you can do correlation table. The correlation table, of course, you can do it on all other regressors. I mean, like all the variables. But see this is like 99.74% correlation. It's a huge correlation. Okay, so how can I overcome that? To overcome that, you're basically gonna say, okay, it seems that these two are connected, so I would better choose one of them, right? I either use population or I use the real disposable income. Because if I add both in the model, then I would be creating multiple units. So you would be better using this one or this model versus this model, and then you start building up your model by adding other additional regressors. Okay. All right, so I'm going to stop here, just give you maybe 10 minutes break. Okay, so now it's 2:07. We're gonna be back at 2:17. Okay, and then when we come back, we're going to continue this multicollinearity part. All right, so I'll be back.
right, so let's continue. So in here, we were talking about multicollinearity. So the other option that we have is that, like, the other option of dealing with multicollinearity, like one of the things I said is to just drop the collinear variable. And we had here an example by saying that population and the real disposable income are correlated. So we can just, and we have checked it and we found that like it's a huge correlation. So one of the ways is to just drop the collinear variable. So let's talk about other possible ways to overcome the problem. So back to the iPad. Okay. So here is we're trying to overcome the multicollinearity problem. So to overcome. So how to overcome? We just, like, I just showed you like one of the ways, but just it doesn't always work. So the one of the ways that we can do is to drop collinear variable. Okay, so, and I'm assuming that this collinear variable is not important. This collinear variable is not related to a certain microeconomic theory that is telling us that we have to include it in the model. However, suppose that I have a model like this. Consumption is equal to beta hat naught plus beta hat 1 income plus beta hat 2 wealth. And I'm sure that wealth and income are correlated. Can I just drop wealth from my regression? Of course not. Can I just drop income from my regression and leave wealth? No. Why? Because this would create something called specification bias, okay? So I can drop the collinear variable as long as they are not by theory connected. Okay, so in theory, in like microeconomic theory, the family budgeting model, is telling us that you have to keep both. And if you drop one of these, then it would run into a problem. Okay, so the problem is called specification bias. You wrongly specified your model. So you can go with dropping the collinear variable as long as it's not leading to another problem, which is specification bias. In the example I showed you, I had a connection between population and real disposable income. I don't have like any basis of a theory for that, so it's okay, we can drop it, okay? But if I do have, then I would run into another problem, like I'm trying to overcome a multicollinearity problem by running into another problem which is not recommended. The second way to overcome is to take a first difference, okay? So taking first difference can overcome the collinearity problem. So if I have a time series model yt is equal to beta 1 or beta naught plus beta 1 x1 t plus beta 2 x2 t plus ut, whatever happens in t also happens in t minus 1, right? So I can always write in t minus 1 last year, beta 0 plus beta 1 x1 t minus 1 plus beta 2 x2 t minus 1 plus u t minus 1. If I subtract 2, this equation, from model 1, then 2 minus 1, I would be able to get rid of the multicollinear, or it's not getting rid, I will be able to reduce the multicollinearity problem. So yt minus 1 is equal to, these two would cancel out, and then I'll be left with beta 1 x 1t minus x 2t minus 1, sorry, this is 1t minus 1 plus beta 2 x 2t minus x 2t minus 1 plus ut minus 2t minus 1. Okay, if you check the multicollinearity here versus here or here, you would have a lower collinearity problem. So taking first difference, or if you run your model in first difference, this is called running the model in first difference, you will be able to find that you're reducing the multicollinearity problem. As you can see, I wrote the model in terms of time series, right? I can get the subtraction between today and yesterday, or today and tomorrow, but I cannot apply it for a cross-sectional model. A cross-sectional model where I have people, I have countries, and in a specific point in time, so I cannot actually subtract person number 2 from person number 1, right? I have to only apply this as long as I have only time series analysis. Okay, so this won't work in the cross-section analysis. The third way to overcome it is just an easy, just increase the sample size. At many times, when you just increase the sample size as much as you can, then you would get rid of the problem. Okay, most of the time you can get rid of the multi-collinearity problem. Okay, so it's a data problem. The multicollinearity is a data problem. So if I can increase the sample size, then I have a wider range of observations taken by my regressors, and this is another way of overcoming the multicollinearity problem. Okay, all right. So our last part is, of course, if you're taking the second level of econometrics, we will do other formal tests, okay, more formal tests that can be done. One of them is called the variance inflation factor, VIF. There is also something called tolerance test, but we will not do like it's outside our scope for econometrics 1. All right, so the next part is, I said we have heteroskedasticity, we have multicollinearity, so we're done with these two. Now let's talk about specification errors. So, specification errors is just covers different types of possible errors that we can run into. One of them, which is very important, which is called omitted variable. Okay, and omitted variable bias. What is an omitted variable bias? Now, suppose I have a model that I'm supposed to estimate. So, suppose I have a model that is y I is equal to alpha 1 plus alpha 2 x1 plus alpha 3 x2 plus ui. Okay, let's call this one as our correct model. And now suppose that you decided to estimate the wrong model, where the wrong model would be equal to beta 1 plus beta 2 x1, we totally forgot about x2, and then this is, let me call a different name for the error term so you're not confused. So this is bi, okay, and this is the wrong model. All right, so now here what we have done is we have forgot or omitted x2, whether I omitted x2 by mistake or whether I omitted x2 intentionally. There are consequences of omitting x2. Okay, so what are the consequences of omitting x2? The consequences of omitting x2 would all depend on whether these two are related or not. If these two are not related at all, if these two are not connected at all, then I won't have any problem estimating beta 2, like beta 2 will be the same as alpha 2, because there is no effect of including or excluding x2. Okay, so the consequences would depend on whether x2 and x1 correlated or not. If they are not correlated, no problem, okay? No omitted variable problem, or in other words, the estimation, the expectation of beta hat 2 would be the same as the expectation of alpha hat 2, and they are the same. So there is no issue because including or excluding x2 does not affect my estimation of beta 2. So if this happens, then you don't have any problem. The problem would happen if they are correlated. So if they are correlated, I will have a bias, I have an omitted problem, and the estimation of these two would not be the same. Okay, and they would not be the same. It might be the case that beta 2 is bigger than alpha 2, could be smaller than alpha 2. We are not sure yet. We have to think about it. Okay, so this problem would be called omitted variable bias under certain conditions. Okay, so when can I call it omitted variable bias? The omitted variable bias has two conditions. Okay? The first condition is there is a correlation between the included and the omitted variable. And if you want to apply it to the example I just gave you, the included is x1, the omitted is x2. So that there is a correlation between these two. And the other condition is x2, or let me say it more generally, is the omitted variable is important to the dependent variable. When I say important, you understand, like statistically significant. So the omitted is x2 and the independent is y. Okay, so the variable that I decided to omit is important. So if this happens and this happens, then we call it omitted variable bias. The bias is coming from the fact that the included and the excluded are connected, and the excluded is also connected with the error term. So it's like here, they are connected, and this is condition number 2. So these two relations, we call this one like number 1, and this is number 2. These two, 1 and 2, actually affect the sign of beta 2. And the sign, of course, in the magnitude. Okay, and we can have a positive bias, we can have a negative bias, and again, like we can have this. Okay. We can have a positive bias, we can have a negative bias. So let's say if, what is my, okay, so suppose that beta 2 is capturing the effect of alpha 3. Okay, so I'm just going to give you an example. So if the correlation between the included and the omitted is positive, and the correlation between the omitted and the dependent variable is positive, then positive times positive would give me a positive bias. And when I say positive bias, then the expectation of beta hat 1, unit I could call it beta hat 1, this is 2. the beta hat 2 would be bigger than the expectation of what is supposed to be, right? So it's absorbing the positive effect. Okay, so let me write it again. Let me just so we have it on one side. We said that our original model is like alpha 1 plus alpha 2 x1 plus alpha 2 x2 plus ui, and we decided to have a wrong model, which is beta 1 plus beta 2 x1 plus vi. If I forget the x2, then this one would be bigger than this one, and this is made under the assumption that the connection between these two is positive, and the connection between these two is positive. Of course, you can make so many different other cases, right? What about that this one is negative? Okay, and this is negative. This is positive, negative times positive. Then I'm going to have a negative bias, right? So this one will be negative. And if this is negative, then I'm going to have this one will be smaller than this one. So it's all about like checking the connection between the two components of the bias and how it's affecting our results. We can have different cases, right? You can have negative, 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 positive, positive, negative, positive, positive. So each multiplication would give me a certain direction: positive bias, negative bias, negative bias, positive bias, right? And this would be showing in the output of the regression results. Okay. So I want you to imagine that if you think about it in terms of the t-statistic, the t-statistic is equal to how beta 2 is far from beta 2 over the standard error of beta hat 2. And I'm just like, you can, of course, remove the 2 and just type it in general like a J or something. And of course, the omitted variable is all about here, the upper part. Unlike the multicollinearity and heteroskedasticity, they were kind of hitting the denominator of the t-statistic more than the numerator. The omitted variable bias is affecting the distance between or the upper part of the t-statistic. Okay, so the consequence of the bias is that I'm going to have misleading results for the t-statistic. Okay? And anything that depends on the t-statistic, the p-value, the confidence interval, all these are going to be giving me misleading results. Okay, so how can I detect whether I have an omitted variable bias or not? I actually have to study very well my model. Make sure what are the most important variables that need to be included in the model, and if I know them, then I have to include them, and making sure that I'm not missing anything. There is also a test, formal test that we will discuss, which is called the reset test, and I'm going to show you this in Stata. Okay. Before I do so, let's continue with the other possible econometric problems. Of course, there are so many econometric problems, but I'm just going to group them into the most important ones that we see a lot. The second one, or I should say, yeah, it's the second one for the specification errors. And this is, I call it A. Okay, so this is one. So let's talk about number 2. So number 2 is if you adopt the wrong, or if you estimate the wrong functional form. Okay, So suppose that your model is supposed to be like this. yi is equal to beta naught plus beta 1 xi plus beta 2 xi squared plus ui. Suppose that this is like the good model, the correct model. For some reason, you decided to estimate it in log. Okay, so natural log of yi is equal to lambda 0 plus lambda 1 xi plus lambda 2 xi squared plus vi, and suppose that this is the wrong model. Okay, of course there would be a bias, right, between the estimated coefficient of the wrong model versus the supposed to be coefficient of the correct model. Same goes here. So if I'm estimating the wrong functional form, then I would run into a bias problem. And my coefficients will be actually unbiased, then they will not be the best linear unbiased estimators, right? So to overcome this problem, we need to, again, study our model, make sure that what people have done in the past. If I'm talking about elasticity model, then I have to include log. If I'm just, my model is linear, then just keep it linear. I also can have a functional form where my model is supposed to be square and I'm estimating a cubic model, things like that. So the solution for this problem, and this problem is kind of short because it's we will expand on it when you take the second level of econometrics. But if the dependent variable is continuous, or if yi is continuous, then we have a topic that we need to study, which is called the non-linear models, because you would have to check whether your model is linear, just like y, or non-linear, like log y, or non-linear, like x squared, x cubed, so you have different variations, or non-linear, which is interaction. So you have like whether interaction, whether it's a cubic, like polynomial, whether it's a logarithmic, or whether just a linear. So you have different options that you need to check your model. And again, this is outside the scope of our course. This is what you will cover in the second level econometrics. What about if my yi is not continuous, or is, we call it binary? And again, when you go to second level of econometrics, you have something called the binary dependent variable model. But for now, we won't be like estimating this model, but this is just something to refer to, like you can refer to this slide when you start the second level of econometrics and you study the binary dependent variable in details. Okay. All right, so this is all about the wrong functional form. The last one, which is you have errors in variables, okay? So it's not the last one, actually, it's number 3. So number 3 is, what about if you run into a problem which is related to errors in variables? When I say any errors in variables, it could be related to mistakes by the researcher. You have done mistakes in downloading the data set, or it's related to, so it could be like a mistake. I downloaded the data set, supposed to be in dollars, and I have a couple of cells in cents, okay? So it could be like a mistake, or you've done the wrong approximation, so you need to check that, or you have incomplete coverage of data set, okay? So all of these can lead you to imprecise measure of your model. So suppose that yi is equal to beta naught plus beta 1 xi plus ui, and suppose that and this is the correct model. And suppose that you decided to estimate this model, which is going to be equal to alpha 0 plus alpha 1 xi, and xi here tilde, which means that imprecise measure. Okay, so this one has a mistake. This one is the imprecise measure of x, okay, plus vi. The vi here would actually include the distance or the difference between the correct measure of x and the wrong measure of x. It, of course, would, like, the vi would have the distance, I mean, like the original error term, right? And would also have the original correct x, right, minus the estimated x, which is the wrong one. Okay, this is 1. I don't know why. This is 1, and this is I, and this is 1, and this is I. Okay? So it would be error term of the original regression, the correct measure of xi times its coefficient, minus the imprecise measure. Okay, so I want you to imagine that if all this is included in the vi, then of course there would be a connection between the imprecise measure and the correct measure. So you kind of relate, like creating, this would be like leading to or creating a connection between xi and vi. And if those are correlated such that xi is correlated with the variance of the error term, then it might lead to heteroskedasticity problem. Okay, and this is going to happen if heteroskedasticity problem, and this might, I'm saying might because we will need to check. There might be some connection, but insignificant, so we will need to check between xi and the variance. Remember, it's not the average, and the variance of the error term. Right? So again, when I say might, because I would need to, I'm not sure, right? Because I need to do a test. Number 4, and the last one, which is in terms of misspecification errors. So number 4, simultaneous causality. Okay. What is simultaneous causality? So we are saying that all the time since the beginning of the semester, we were saying, okay, I have this model, and my, or the assumption is the effect goes this way, right? X affects Y. We never thought about the impact of Y on X, right? We never, like, it's always this way. However, simultaneous causality is actually saying that there might be an effect also coming from Y to X. So X affects Y and Y affects X. So this reverse, we call it reverse causality. The reverse causality can be represented by an equation such that xi is also equal to lambda 0 plus lambda 1 yi plus vi. Okay? And if, for example, if ui, which is right here, if this ui is negative and it's in the equation of yi, then this yi will decrease. And if lambda is positive and this one decreases, then also x I would also fall, right? So I'm kind of creating a connection between the error terms, but really bad terms of color. I'm really creating a connection between the error term and the x, right? Because the error term affects y Y affects X. So I have a connection between this and this. And again, I need to check because this might be also create heteroskedasticity problem. And I'm saying might because I need to check between xi and the variance of the error term. Okay, so misspecification errors can lead us into other econometric problems, right? So we need to kind of make sure that we are avoiding all these possible econometric problems. In order to avoid, or the solution for simultaneous causality is actually you need to use the correct methodology. What is the correct methodology? The correct methodology is called instrumental variable regression. And the instrumental variable regression is again out of the scope of Econometrics 1, and this is something that you will cover in details when you go to the second level of Econometrics. All right. So this is all about the misspecification errors. Right? What I'm going to do now is I'm going to share with you this data, and we're going to apply what we have learned into certain example. Okay, so let's see. So back to this data. And all right, so what we have done so far is we have, so multicollinearity, we have done that. We have done heteroskedasticity. We have done the example using college distance data set. Okay, we still have the autocorrelation of errors, so I'm going to cover that. You know what? I'm sorry, let me go back to the slides. And so let me go back here because I forgot about the autocorrelation, which is in here. Again, this is another problem, which is the autocorrelated errors. Autocorrelated errors means that OLS assumes that you don't have any autocorrelation of residuals between one year to the next, okay? So whatever errors today, they are not connected with errors tomorrow. Whatever the residuals of the Y regression today, they are not connected with the residuals of Y regression tomorrow, and so on. And this is basically in time period, okay? So we're talking about time series analysis. So we need to, if we have some correlation over time, then we are actually violating the OLS assumption, okay? You will see that reflected in the t-statistic. There will be like too large for some variables and appears significant while they are not statistically significant. You can check it through the connection of the error term over time, okay? So if I see that if I have the x variable is time, and this is the error term, and I see like going up and down and like cycles, then they are not constant. Right? If they are kind of moving just dots on one around, let's say the 5, then they would be constant. So this, if I have errors that are autocorrelated, right, like here or like here, they change with the x, then they are actually not independent, then these two are violating the OLS assumption. This graph here is not a violation because this is what the OLS assumes. They assume that they are independent. Okay? So how can we check that? There is a formal test called the Durbin-Watson statistic. Each test, as you know, has a certain null hypothesis and an alternative hypothesis. So the null hypothesis is always the good news, okay? So the errors are not correlated. And then the alternative is that we have a problem. We have autocorrelation in the model. And of course, if I'm looking at here and I want to have like a good news, or I want to have like no correlation, then I hope to get a high p-value. or I hope to get a small Durbin-Watson statistic that is falling below the critical value. So the Durbin-Watson statistic is actually made out of the errors that you have. So again, you extract the residues, you get the difference between the error term today, error term yesterday, square, sum, divided by the SSR, the sum of the squared residues. This is the SSR that you know. This test statistic has a certain range from 0 to 4. It has a certain table that usually you won't find it in your textbook, but you can find it online. And the benchmark would be like number 2. If I get a Durbin-Watson statistic that is less than 2, you would say, okay, I have positive autocorrelation for my error term. If it's greater than 2, then you have a negative autocorrelation. Okay, so let's see if I have the test here, and it has a lower limit and it has an upper limit, and you can always have a look at the chart in order to determine whether you're getting a positive correlation or not. Okay, let's see here. This is just an example. These are the two components of the Durbin-Watson. The upper part has this number, the lower part has this number. You divide this by this, you get the number right here. And how can I make sense out of this number? I have to check the table, the Durbin-Watson table, get the critical value. Okay, and then I'm going to show you the table. So, but here, let's say you check the Durbin-Watson table and you find that the 1.00494 is actually below the critical value. So as you can see it here, it's below the critical value of the lower limit. So this is a rejection region. So you reject the null. What is the null? This is a bad news, right? So you reject the null that you have a correlation, right? So that means you have to conclude that you have significant autocorrelation. Okay. You can also refer to the number 2. Okay. If it is less than 2, then it's positive. If it's greater than it's negative, and of course this number is less, so it's a positive, significant positive autocorrelation. All right. So I'm going to show you in Stata how to do the Durbin-Watson test. Okay, so let me show you here. So autocorrelation, so you have, okay, so let's clear, declare, regress consumption, and then the command for the Durbin-Watson is a state d Watson, okay, and then you get it this way. And what you have here is a certain number that you need to find the critical value. So I found, actually, because you don't have it on your textbook, I found like you have so many versions of the table online. So I got like this one, and so how can you read it? So you basically go to the table. What is this? Oh. Okay, and then the Durbin-Watson table has like the lower limit, the upper limit. Let's say this is 5%. I need to know what is my sample size. So when you go here, your sample size is 37. Okay, and I'm testing one coefficient. So you go here with K1 because I have only one X, and you go to 37 with 1. So you get the lower limit 1.42 and 1.53. I wrote them here for you, so and I'm going to post this for you on the week 13. So I have N37 lower and upper, and then what I'm going to conclude is this number is much smaller than this number, and we conclude that we have a positive significant autocorrelation. Okay, so this is all that you need to do. You just go to the table, and again, you have different versions of the table. They are the same numbers. I found this online, but you can find other references. They all have the same number. Okay, so what else? Before we, okay, I just want to tell you something. If I do have a significant autocorrelation based on Durbin-Watson, what we can do? We can correct for this autocorrelation, and again, this is a simple way of correction. We have more challenging ways of correcting the autocorrelation, but I'm going to just go over the easy one. Okay, this is what you have for your course. So we have to do 2 steps. If I realize that I have a significant autocorrelation, then I have to create something called the R. What is R? R is just a certain parameter that is equal to 1 minus the Durbin-Watson test over 2. And this is a correction. Okay? So you estimate an autocorrelation parameter using the Durbin-Watson test. Next, what you need to do is you estimate the least squares regression. Your dependent variable now is corrected. It's allowing for this correlation, right? So you have the R parameter attached to the first lag. First lag is like the last year, okay, or last period. The first lag of Y, so R times the first lag of Y, R times the first lag of X1, same for X2 and same for Xk. And your dependent variable now is run in first difference, but it's corrected using the correction parameter using Durbin-Watson. You are going to re-estimate the model using these corrections, and you are going to use the parameters of this estimated model in order to make inference or analysis about your results. For the intercept, as you can see here, we didn't mention anything about the intercept. For the intercept, you can correct it by dividing by 1 minus R. Okay? And this way, you are supposed to be correcting for the possible autocorrelation. It's not the possible, it's the significant, I should say, the significant positive autocorrelation that we found on the example I just mentioned. Okay, whether it's positive, whether it's negative, you can still be using this correction method. Okay. Of course, this is one way that you can use, but of course there are different other ways that can be used to correct for the autocorrelation between the errors. But we're going to stick to this only method. All right, for the Stata. The last thing that we're gonna do is application to multicollinearity and specification errors. Okay, we're going to be using a data which is called highway quality, and you're trying to estimate how the quality of highways is affected by different firms that are building the highways and other possible factors affecting the highways. So to get more details about the data set, I have the description of the data set right here, and it's going to be posted on Sakai. So the quality of roads data set description. Your dependent variable is called quality. Okay, so the quality variable is measured as by an independent agency. It has a higher number, maximum of 300. Lower number is 0, which reflects the worst shape, and the maximum, which is 300, reflects the better shape. We have 3 different names of firms: ABC, Boraz, and Ketis, and these are all firms that are actually building or laying the highway. Okay, and then we have different variables: the cost per mile paid the last time the road was resurfaced. You have how many exits per 10 miles on the highway, whether this is affecting the highway quality. We will check that. We have the number of car miles driven daily on a country's highway, how it's affected its quality. How many trucks, like, is there any difference between cars and trucks? So we need to check that. Latitude, which is the geographic coordinate that specifies the north-south position of a point. on the Earth's surface, the age of the road, how it's affecting its quality, and then the percent of miles, maker, road signs with significant damage. Okay, so sig damage, significant damage. All right, so we're trying to estimate that. Of course, okay, let's clear and get the data set. When you check the data set here, the column firm is just some names, right? Stata will not understand that. As you can see, it's in red because Stata cannot understand the letters. They just need number. So we need to move, or I should say transfer these names into numbers. So one way to do that, there are two ways. So I have one way here and another way here. Choose whatever you like, but I chose this one. So we're going to tabulate or rename these variables by just numbers, right? So we're going to firm 1 is ABC, firm 2 is Boras, firm 3 is, and so on. Or you can just move them into like this by creating a certain dummy variable that takes 1 if the firm is ABC, takes 1 if and 0 otherwise. Boras takes 1 if the firm is Boras and 0 otherwise, and so on. Okay, and then we have the information about the data. You can summarize it and describe it. Let's check here. Number one thing that we need to do is, suppose that this is my main model, okay? The quality, the three types of firms I have, right? And then the different variables we have, and we run this main model. So when I run this main model, like it has everything. So when I run this main model and I check here, okay, these are statistically significant. The exit per mile is insignificant, cars per mile is insignificant, trucks is insignificant. The others are significant and expected in terms of sign. So whatever is insignificant, I really need to find out why. Is it related to a problem, an econometric problem, or is it something like multicollinearity, something is redundant, and so on. So the first concerning result is actually this one, okay, which is the estimate on the number of exits per 10 miles of highway roads in the county, okay? And this result is kind of like you need to figure out why is it insignificant, right? So when you check at the p-value, it's almost 0.87. It's insignificant. The point estimate that you get is relatively low. So you're talking about a variable that has an impact of only almost 0.9. Okay, what does 0.9 means? If I actually check the values taken by this exit per mile, let's see here. I should like have summarize. So let's see what about exit per mile here. So the exit per mile is a value of 1, and this is the highest value. Even if you go with the highest value, does that a significant impact? So let's take 5.9. So is 5.9 times, right, times the 0.09, which would be equal to about 0.531. Is it significant impact on the quality? I don't think so, right? So in other words, the given estimate, which is approximately 0.09, it's telling us that the county with the least number of exits sees its expected quality falls by 0.09, while the county with the most number of exits, which is the maximum value of exits, sees its expected value falling by 0.531. What is 0.531? It's actually the multiplication of 5.9, which is the maximum of the exits per mile, times 0.09. I say that this one is a very small difference in the range, right, of the quality variables. So it doesn't seem to be an important impact, right? It's kind of small. So I can probably minimize my model by removing this. Okay, so one of the things that you can do here is by checking the results and it seems to be insignificant, and you think about it and you go to, okay, what would be the highest impact of this variable? I go to its maximum value, 5.9. So 5.9 multiplied times this, it's just not nothing, right? It's only 0.531 effect on the quality. So I can just make my life easier and just removing the exit per mile. Okay, it doesn't make any difference. I mean, like, it's not that important. So what you had here is the exit per mile. What you have here is we have dropped it. Okay, it's not there. So you can run your regression without it. Now check what's going on here. Significant. What about these two? Cars per mile, trucks per mile. What's the definition of that? So the definition here is telling me that the number of car miles driven daily on the county's highway, the number of truck miles driven daily on the county. So it seems to be some multicollinearity problem, right? So you can check that by actually repeating this regression twice. One time with only this variable, another time with only this variable, and see how it's affecting. So you can actually also check the correlation here. So let's see. So the cars per mile and the trucks per mile. So this one, okay, see this one. It's a huge, right? So it's a huge correlation between the two. So we seem to have a multicollinearity problem between the cars per mile and the trucks per mile. You can keep checking by running two separate regressions, one time with only this variable, another time with only this variable, trucks and cars. And you will be able to find that you're actually getting similar results, okay? Why I have this one is omitted. This is because I have 3 dummy variables, and these 3 dummy variables, their linear combination is creating perfect multicollinearity, right? Because if one is 1, the others are 0. If one is 1, the others are 0. The linear combination is a column of 1. So when the column of 1 is created by the 3 dummies, it's perfectly collinear with the constant of the regression. So I actually should be removing one of them. Okay, so this is something that we can remove. And then let's run again. It was already omitted, but then in the one that I just mentioned, which is the linear combination that is equal to 1, is highly correlated with the vector of 1s for the intercept, creating an econometric problem called the dummy variable trap. And again, this is you will discuss in details next level. Anyway, so now we have we were able to get rid of the omitted variable that you were able to see here. Now, what we can see here is all the variables are statistically significant. Same here, right? But if I include both together, trucks per mile and cars per mile, I'm getting redundant results. They are perfectly collinear. So your best option would be like choose one, either this one or this one. Okay, so it's up to you. I decided to use the cars per mile, so I have dropped the trucks per mile, and I let this one to be my main. Oh, I'm sorry, I should have also removed the ABC. Okay, and then I let this one to be my regression, or my main, or my base regression. Okay, so next, there is an example that I wanna, the test I wanna show you, which is called the Ramsey, let me just save. And this one is called the reset test, which is the Ramsey regression specification test. And this test is used in order to see if I have some omitted variable bias in my regression. And this one is done by doing the regression. And again, I'm going to remove the ABC to avoid the dummy variable trap. You have also other option. If I want to keep ABC, I have to remove the intercept, because the perfect collinearity is happening between ABC and the intercept, okay? ABC, Boras, and the third variable and the intercept. Okay, let me, no, actually, so I just want to make it consistent. Okay, so I have these two firms are here. I just want to make it consistent model. Okay, so now I'm removing ABC and I have the two other firms. I have two options, either to have the three firms and no intercept, or drop the intercept, or keep the intercept and the three firms. Now here I'm using two firms and keeping the intercept. How this test works, you estimate the model, you get your error term, you create the square, the cube, the fourth power of the why I'm saying the error term, I should say the dependent variable, which is the quality hat, okay, quality hat. So you get the quality, you do the regression, you get quality hat, or you call it y hat, and then quality square, quality cube, quality to the power 4, and after you're done, you add them into the model. So you do it this way, right? And okay. And then what you need to do is the reset test is actually testing, I don't have it here, but it's testing the joint statistical significance. So whether, so you perform a test PRM is the F test. So you do it this way, and what is it telling me? There is almost a 0 probability, right? Very, very small probability. That it's a 0.45 probability, okay? So it's a small probability that these are equal to 0. In other words, I have to keep them in the model, because if I don't keep them in the model, I have omitted variable bias. So this test is telling me you need to keep the nonlinear form of the quality hat or the y hat into your model, okay? We have also the command, the OV test. See, it's getting the same result. So it's one, like you either do it manually or you do the OV test. In both, they would give you the same result. So this is how it works. You just create your average, you create your powers, and then you include them in the regression, and then you perform the F test. And based on the result, you're saying there is a low probability that these are equal to 0. In other words, keep them in the model. And just notice, we're testing 3 restrictions, right? Which are the 3 restrictions here. Okay, and we're getting the test statistic 438 p-value, same as this one. So you can do it manually, or you can do it by the just one shot, which is OV test command will do it for you. Okay, so this test is just telling us that we can we have omitted variable bias in the model, and we have to include the nonlinear terms of the dependent variable or the predicted dependent variable. All right, so I'm going to stop here, and we're going to continue next week. Okay, and stay safe and stay well, and then I'll meet you again on Zoom next week. All right. If you have any question, please let me know by email, or you can post on the discussion forum. All right. Enjoy the rest of your day.